Alright, guys, so today I'm going to be presenting my Astronomy Final project. And so, pretty much, I'm going to give you guys a breakdown, and I'm going to give you guys a little lesson on tectonic plates, earthquakes, tsunamis, hurricanes, and telescopes. And I'm going to go ahead and break it down into a couple lessons so that way you guys can go ahead and follow along. So, we're going to begin with plate tectonics. So, essentially, what are plate tectonics? Plate tectonics is a scientific theory that pretty much explains how landforms on our planet are created. And this is as a result of Earth's subterranean movements. So how do plate tectonics work? So pretty much Earth's lithosphere is broken up into large rocky plates, in which these plates sit on top of the asthenosphere, which is also a molten layer of rock. And these plates tend to move at different rates, but these rates can range from 2 to 15 centimeters or 1 to 6 inches per year. So then we're going to move into continental drift. Well, when we talk about continental drift, it is a theory not 100% proven, but there is a lot of evidence that helps support this claim. And this theory was hypothesized by Alfred Wegener in 1912. And he suggested that about 200 million years ago, the supercontinent Pangaea began to break apart and move into the continents that we know today. And so pretty much on the chart on the right, we're going to go ahead and start off with Pangaea, which is what more or less it looked like about 225 million years ago. And then about 75 million years later, we have the two supercontinents. We have Laurasia and Gondwana, which the top is modern-day North America and Asia, with the bottom being South America, Africa, Antarctica, and Australia. And then, about 50 million years later, then this continent starts separating a little bit more, in which we know as today what more or less looks like our continents and modern-day civilization. And then finally, on the bottom right corner, we go ahead and move to what Earth looks like today. So pretty much, are there any consequences of plate tectonics? And the answer is yes. So plate tectonics move only a few centimeters per year, but are essentially the root of all natural disasters, which can lead to earthquakes, tsunamis, volcanoes, and pretty much every type of natural disaster, which have huge repercussions. Here displayed is the earthquake that took place on March 11th, 2011 in Tohoku, which was catastrophic, just off the northeast coast of Japan. And essentially here on the chart on the left, it displays the 4 plates, but mainly targeting the Eurasian plate, in which you can see all of the force and the energy which was derived from this earthquake that led to a catastrophic disaster. And here on the right side, we go ahead and dive deep into what Tohoku looked prior and after the earthquake. As you can see on the right side, it looks prospering, it looks like a standard, city. And then after this horrible earthquake, just left in ruins, with floods. And as you can see, the pictures are just very devastational. Then it gets tied into, earthquakes and tsunamis. And this is pretty much following off, piggybacking off of tectonic plates. Like I mentioned, tectonic plates are pretty much the root of everything, and just kind of, it allows for all these different types of things to derive from. Earthquakes are a violent shaking of the ground that time can cause great destruction. As a result, within the movements of the Earth's crust or volcanic action. A tsunami is a series of ocean waves which can have large disturbances to ocean waters and have powerful storm surges that can harm environments and civilizations. And how are they connected? So essentially, earthquakes and tsunamis are connected due to the sudden, abrupt shift of a large area on the seafloor. This disturbance allows for tsunamis to occur as the amount of energy and force created from the underwater earthquake leads to the tsunami forming and a huge shockwave moving water at a very fast pace. So, how are earthquakes formed? Earthquakes are formed by plates getting stuck together, and with the amount of friction and the stress from these plates releases an undeniable immense amount of energy and waves that travel through Earth's crust, which cause that shaking that we feel here within our houses, schools, any type of environment, just, on the top. And here, here's these charts that pretty much kind of break it down and give you a better visualization of what I am talking about. So pretty much here on the left, the epicenter and the focus is pretty much where the earthquake is derived from, with the surrounding circles essentially showing the shock wave in which the energy is moving, and gives you an idealization of what the plates more or less look like on a better chart shown. Then on the right side, we have another chart that pretty much displays the energy and in which way it is moving and the direction it's headed. So how are earthquakes measured? So earthquakes are measured on a Richter scale, which pretty much is a scale from 1 to 10, obviously 1 being the least powerful and 10 being the most powerful. We have not yet endured a level 10 earthquake thus far, but we are not supposed to for a very long time. Earthquakes like that don't happen often. We more or less feel, micro and minor earthquakes ranging from 1 to about a 4, and those can happen in our everyday lives, but it is minimal shaking, minimal destruction. But as you start getting into the higher levels, moderate and stronger earthquakes, that's when, cracks in buildings can occur and just more devastational damage. And then when you start getting to the major and great types of earthquakes, that is when catastrophes occur, deaths arise, and just it is not an overall great thing. It is very, very bad. So how are tsunamis formed? Tsunamis are formed by a cause of energy or an underwater earthquake. When an earthquake occurs, it causes the energy from the seafloor to move up and down, and which displaces a large amount of water and creating a wave. This wave can travel at immense speeds with the velocity reaching up to 500 miles an hour. And here's a chart pretty much breaking down the tsunami into 5 levels, beginning with the activation of this underwater earthquake, then level 2, building itself up and starting to bounce those water molecules from water molecules to pretty much pass on the energy. Then formation, the wave is starting to form and it's starting to build that height and that destructive, force that it carries with it. And then step 4, the approach, where it is approaching whatever is in its path. And then finally, level 5 impacts whatever stands in its way and absolutely just tears apart anything in its path. So here are the effects of earthquakes and tsunamis. Earthquakes cause direct damage when taking shaking, weaknesses, and collapsing buildings and infrastructures not built to withstand tremors. Cities along coastlines have attempted to build seawalls to avoid such catastrophic damage, but seawalls are no match for the power that these natural disasters, the energy and the strength that they possess. So here are a couple of images that essentially display the overall damage that these natural disasters occur. Here on the left, we have an image from a tsunami taking action in Japan, just all that water flooding over that seawall and pretty much wiping out anything in its path. In the second photo in the middle is an aftermath of an earthquake in Nepal, pretty much showing how that buildings surrounding it is in straight ruins just from the amount of energy that was displayed. And lastly, the image on the right side is an aftermath of a tsunami in Indonesia. As you can see, is just horrible. As you can see, all the water just stagnant, and everything that stood in its path is just non-existent anymore. As you can see, just a bunch of rubble and garbage and half torn apart buildings and just an overall ugly scene. Then we move into hurricanes. So hurricanes are generally known as tropical cyclones and are developed over subtropical waters, and they gain their energy from warm ocean waters and can move towards land at speeds of up to 72 miles an hour. Hurricanes can form due to disturbances within areas of the ocean with warm temperature of at least 80 degrees Fahrenheit. Because of low pressure caused by the warm seas and temperatures continue to rising within the oceans, the storm can form. And therefore, it is declared a hurricane. So there is also a scale to measure hurricanes known as the Saffir-Simpson hurricane wind scale. This is used to classify hurricanes and measures them from its wind speeds to determine the intensity of a hurricane, in which there are 5 levels of this scale, but they are known as categories. So pretty much category 1 is roughly from 74 miles an hour to 95 miles an hour with a storm surge of 4 to 5, which can definitely wipe out things in its path, but is not the most devastational. And then as we move to category 5, which has wind speeds over 155 miles an hour and over 18 feet of storm surge, which just undeniably will annihilate everything in its path. It has galloped cities and towns and anything that stands in the path of a hurricane. And here in this chart pretty much just depicts what happens in these hurricanes when they occur. As you can see from level 1 with minimal water levels rising to category 5, where everything that stood in the path of this hurricane just was swallowed. So, effects of hurricanes. If hurricanes reach land, it causes damage that can be catastrophic, and storm surges that can rise to 20 feet and extend for about 100 miles. The winds not only cause massive damage, but also spawn tornadoes and include excessive rainfall that can cause floods that can occur miles inland. Here are a couple of images to give you a better depiction of what hurricanes look like and consist of. So here on the left side is a space view of a hurricane forming. So pretty much it is taken from space on a satellite and shows the sheer size of a hurricane. And in the middle is a hurricane in action, as you can see the water beneath with all the rainfall, which is pouring down on these homes. And as you can see the immense force of the winds from the trees swaying from just the pure force of the hurricane. And then finally, on the right side is the aftermath of a hurricane, in which the buildings are torn apart, falling into the storm surge and the flood, and just torn apart by the wind and the water that occurred. And did you know that hurricanes, typhoons, and cyclones are all the same thing, just called different names depending on where they're formed? In the North Atlantic and Central and Eastern North Pacific, these storms are called hurricanes. In the Western and North Pacific, they're called typhoons. And in the South Pacific and Indian Ocean, they are called cyclones. Then, finally, we move into astronomical telescopes. So, what are the purpose of an astronomical telescope? So, the purpose of these telescopes are to collect the faint light from an astronomical source and to focus the light into a point or an image. So, how do telescopes work? These telescopes work on the principle of when an object can be magnified and is placed at a large distance from the objective lens of the telescope and is inverted in the magnified image of the object that is formed at the least distance of the distinct vision from the eye held close to the eyepiece. So what is the difference between astronomical telescopes versus ordinary telescopes? Astronomical telescopes can observe stars beyond the Earth, while ordinary telescopes only look at objects that are closer. Ordinary telescopes have only one refraction type, while astronomical telescopes are not limited to one style or order to achieve a longer observation distance and better imaging effect. Astronomical telescopes are specifically designed for viewing the sky, while ordinary telescopes are only designed primarily to look at things on the ground. Astronomical telescopes are large and complex, while ordinary telescopes are smaller and more compact. So, here are the 4 different types of astronomical telescopes: refracting telescopes, reflecting telescopes, compound telescopes, and radio, X-ray, and gamma ray telescopes. So here are a couple of images of these different types of telescopes, so that way you can better see these telescopes and understand the parts in which they possess to understand their specific function. So we begin with refracting telescopes. Refracting telescopes is a lens, just like an eyeglass, that bends the light through, that passes through it to make things less blurry. And it makes the things that are far away to seem closer. So the small lens magnifies and focuses light for the eyes, in which the light is focused on the objective lens, and the large lens gathers and bends the light for us to see. Then we move to reflecting telescopes. Reflecting telescopes have the light from the celestial body that enters through, and which is reflected off the secondary mirror, and then the primary mirror, and which then is displayed within the eyepiece. The small mirror reflects the light and image into the eyepiece, and the large mirror gathers the reflective light. And finally, we end with compound telescopes. Compound telescopes gather the celestial light, and then the correcting lens, and then the secondary mirror and primary mirror all advocate for the overall depiction of the image that is displayed within the lens or the eyepiece. Then we have the radio telescope. And the radio telescope is more peculiar. The radio telescope, its primary parabolic reflector surface has a specific function, while all the other parts of this radio telescope do as well. The distant celestial body is able to be received from the incoming radio waves that it possesses, which the subreflector and the feed horn distribute for carrying the signal to the control room for the processing, and which this is a little bit more technical, as computer and recording devices and receiver and amplifiers are used and put on video display for an analysis with magnetic tape. Then we go into X-ray telescopes, which are used for pretty much more specifically are used to see doubly reflected X-rays with a narrow field of view, with a focal surface that allows for this to be portrayed.